Have you ever stopped to think about what's really going on inside your computer? I mean, we use them every day, and what they do feels like pure magic. But it's not. It's this incredible high-speed dance of logic happening billions of times a second. So how does it all actually work? All right, let's pull back the curtain and find out.
I mean, seriously, think about it. You click an icon to open an app and poof, it's just there. It's instant. But what's the secret sauce? What happens in that split second between your click and the result? There's a whole secret journey your command goes on, deep inside the machine.
And that's exactly what we're going to do. We're going to follow one single command, step by step, as it zips through the heart of your computer. Trust me, by the end of this, that so-called magic is going to make a whole lot more sense.
Okay, so our journey starts at the very top. We're heading straight to the command center, the mastermind of the whole show. Let's meet the CPU, the Central Processing Unit. And when we say it's the brain, we are not kidding. It's got all the essential circuitry to handle three key jobs: process the information you give it, store whatever data it's working on, and then spit out the final results. Literally, every single thing your computer does is being directed by this one powerful chip.
But here's where it gets really interesting. The CPU isn't just one single thing. It's more like a super efficient team working together. You've got the control unit, that's the director calling all the shots. Then there's the arithmetic logic unit, or ALU. That's the team's math whiz. Registers? Think of those as a tiny, lightning-fast sticky note for whatever the CPU is working on right this second. And cache is a small bank of high-speed memory for stuff it needs to grab all the time. So let's start with the director, the one in charge.
All right, we're diving straight into the command center. This is where every instruction gets its marching orders. You can think of the control unit as the ultimate air traffic controller for all the data zipping around inside the system.
So the control unit has this really important three-part job that it does over and over. First, it fetches the next instruction from the computer's memory. Second, it decodes that instruction to figure out what needs to be done. Is it a math problem? Does data need to be moved around? And third, it sends signals to the other components, like the ALU, to actually carry out the command. It's this constant, relentless cycle: fetch, decode, execute. Now, it turns out not all control units are built the same way. A hardwired unit has its instructions physically set in stone, right in the circuits. It's incredibly fast, but totally inflexible. A microprogrammed unit, though, is more like having a rewritable playbook. Its instructions are stored in a special memory, which makes it way more flexible and easier to update, even if it's a tiny bit slower. So let's explore that playbook idea. Yeah, this whole playbook concept is pretty genius. It's how computers take big, complex jobs and chop them down into a bunch of tiny, manageable steps. And these steps are called microprograms.
So a microprogram is basically just a sequence of super basic commands called microinstructions that are all stored in a special little memory right there on the CPU. So when you tell the computer to do something that seems complicated, the control unit just looks up the right microprogram in its playbook and follows the simple step-by-step guide.
Let's make this real with a simple example adding two numbers. To you and me, that's one action. But to the CPU, it's a four-step microprogram. First, it has to load the first number from memory. Then it has to load the second one. Only then does it send them both to the ALU to actually do the addition. And finally, it has to store the results somewhere. Every single command is broken down into these fundamental building blocks.
You've probably noticed we keep mentioning memory. The CPU is constantly fetching from memory, storing to memory. But here's the thing. It's not just one big pool of memory. There's a whole tiered system, and its clever design is the real secret to making our powerful computers affordable.
Which kind of begs the question, right? If the CPU is this blazing fast brain, why can't it just use one gigantic, super fast memory for everything? Why all the complexity? Well, the answer is a classic engineering trade-off between three things: speed, size, and cost.
The best way to think of it is like your office. The cache is like a sticky note on your monitor. It's tiny, but it has the exact info you need right now. Main memory, or RAM, is like your desk drawer. It holds everything you're actively working on, and auxiliary memory, your hard drive, is like the giant archive room down the hall. It holds everything, but it takes time to go get something. The CPU needs this whole team just to keep from sitting around waiting for data. And here you can really see that trade-off in action. Cache is the fastest, but it's incredibly expensive, and so you only get a tiny amount. Auxiliary storage is massive and cheap, but it's the slowest. RAM sits right in the middle. By combining them in this clever hierarchy, a computer gets the performance of having a huge, fast memory, but without a price tag that would make your eyes water. This layered system is a brilliant compromise, and it's what makes modern computing possible.
All right, so we've met the brain, its internal team, and the entire memory department. Now let's put it all together and watch this high-speed symphony in action, from start to finish.
So this is the complete journey we promised. First, the control unit fetches the instruction, pulling it from RAM. Second, it decodes it, figuring out what to do. Third, it directs the ALU or another component to execute the command following the steps in its microprogram playbook. And finally, the result is stored, maybe in a super-fast register or back in memory. That is the fundamental heartbeat of computing.
And here is the truly mind-blowing part. That 4-step cycle we just described, a modern CPU can perform that cycle billions of times, every single second. That incredible speed is what transforms this very mechanical process into an experience that feels instantaneous, like magic. So the next time you click an icon, just for a second, remember that silent symphony, that constant cycle of fetching, decoding, and executing happening at an unimaginable speed. It really makes you wonder, with computers already performing billions of operations per second, what new frontiers will they conquer as they become even faster? What new possibilities are just waiting to be unlocked?